Hi everybody, I just want to talk about linear combinations and this formula. So first remember that a vector is something that we can add, and that sort of looks like if this is v and this is w, these are two vectors, then we can add them by putting the tail of w at the tip of v, and then this resulting final minus initial is v plus w. Okay, and so one thing is it's important to be flexible and just move these vectors around. Seen differently, we could have based them at the same point and said, if v is like that and w is like that, then we first move in v and then we move in w and we end up here. And so that is the vector v plus w right there. But another way to think about this is we first move in w and then we move in v, and we get the same vector, v plus w. So this is vector addition plus of vectors, like a vector and a vector. Let me move that to the side. And then there's a vector scaling. So if we have a vector, like if this is v, then 2v is like that. And minus 2v is like this. And minus 3v is like that. And a half v is like that. And so these are the only things we can do with vectors, is add and scale them. We can add vectors, we can scale vectors. But then we could add them after scaling them. We could scale both of them and then add them. And this brings us to linear combinations. Okay, so let me move this. And in particular, this symbol shouldn't be scary. It's just a shorter way of writing it, because you don't want to sit there. And what it really means is C1 V1 plus C2 V2 plus C3 V3 plus. And there's some amount. I could have said like 4 there, and then we would have had one more term. So you could write the number of terms. The terms are the things that you add together. And there's 4 terms. And we plus them. Okay, so this is what it is. And now, what could this really look like? So first, each of the CIs is a real number. They're the scalars. The VIs are vectors. And they could be in any Rn. So in particular, let's take n to be 2. Then we'd have like maybe a 2 times the vector 1 minus 1 plus a 3 times the vector 8, 0. Plus negative 4, so C3 is negative 4. They're each real numbers, times the vector 7, 5. Plus, maybe it's a pi. Pi is a real number, is C4, times like 2, 3. Okay? But if the v's are in R3 instead, then it would look something else. It'd be like, I'd have to pick different vectors. Now, v2 has to be a vector in R3. And I need some scalar, and then I could take the same scalars. So the same scalars can work, but just in vectors of a different dimension. And notice I can't do something like this. Like, this makes no sense. Because you can't add a 2-dimensional vector to a 3-dimensional vector. I guess you could like append a 0, but that's a different vector. It's in a different space. So be careful about that and know that each of these v's has to be a vector in the same size space. In particular, like the v's, the vi could be in R to the 1, and this will come up, is, and what would that look like? Well, then our vector just has one component. And now we have just one component. Maybe this one has a negative 1 plus pi times maybe this one has a 17. And so, now we're just multiplying numbers adding them to multiplication, adding them to a multiplication, adding them to a multiplication of numbers. And there's really no difference whether we think about this number as a number or as a vector, because R1 is the same as R. And so I just wanted to point this out, that and that's why this notation is so useful, because we can hide these details. We can hide the details. In particular, like, we can hide even the components of the vector, and we can just think about this, right? And so that's why it's useful to hide the details and free our mind of that baggage, free our mind to think of the more difficult conceptual things that we are using this for, right? Like derivatives and tangent spaces of curves in higher dimensions. So, yeah. One more thing. This expression, at the end, what is it? Do we get a real number? Do we get a vector? And the answer is we get a vector. All this, we could actually add it up. We could actually do this linear combination. Multiply and add to all these vectors. We're adding them together, and we'd get one vector. So in this case, what would we get? Well, a vector has two components, right? So this thing becomes a vector. Well, a vector in R2, in this case, has two components. And the first one is 2 plus 24 minus 28 plus 2 pi. And that number goes there. Then the second component, what's this number? Well, the second number should be negative 2 plus 0 minus 20 plus 3 pi. That's some number, and it goes there. And so this thing, at the end of the day, is a vector of the appropriate size. Vectors are nice because we can only add them and scale them. And so this is all we can do. Just do those two things a bunch of times. But this idea is used everywhere in science.